Well, hello everybody. Today I'm going to talk about Riemannic number of a graph. So, um, yeah, so let's get started. Okay, all right, here it is. So I'm going to talk about Riemannic number of a graph, which is a coloring of a graph. I picked this topic because I believe that I want to show that math sometimes can be fun and you don't need a lot of high knowledge in order to do some math tasks, and even not even mathematicians sometimes do things that are uh, very essential for math, and yeah, just like even other mathematicians can do really good stuff for math. So let's get started. So topic of my is Riemannic number of a graph. So what is a graph? So in math, we call graph a set of vertices, some of which are connected, and we call these connections edges. As you can see on the picture, edges are painted in black, and vertices are painted in blue. So some of them connected, some not. So this is how the graph looks like. Okay, let's keep moving. So what is the proper coloring of a graph? So let's define the proper coloring of a graph. Like we call the proper coloring of vertices if there are no two adjustment vertices of the same color. So which just means that we paint vertices, and if two of them have the same color, they should not have the same. They should not have edge. They should not be connected. So as you can see in the picture, I have three green ones, and they're not connected, and the rest are different, like yellow, orange, and red, so they can be connected. Okay, so what is the Fermatic number? Fermatic number Q of G, where G is graph, is the minimum number of colors needed for proper coloring of a graph. So as you can see for this graph, it is free, so we cannot color it in two or one color. In one, obviously, we cannot color it. Why we cannot color it in two? Because if you can see, there is a triangle there, which have all connected. So if we just want to paint it in two, then two of the or three of the vertices is going to be the same color, and they're connected. So we cannot do that. So that's why the minimum is three. And as you can see, three is working totally. We have green, blue, and red. None blue connected, none green connected, none the red connected. So let's talk about chromatic polynomial. What is a chromatic polynomial? So it was invented by George David Birkhoff in 1912. He was trying to solve the four-color theorem, which we're going to talk later. So chromatic polynomial is a polynomial of k, where k is a number of colors. It represents the number of proper coloring of a graph. So it means that in how many ways we could color our graphs properly. So there are going to be different ways we can color it. So which means that, yeah, if we want to know how many colors, how many ways we could color this graph in k colors, we just plug in k, the value k in the polynomial, and we get the answer. So for example, for this graph, the chromatic polynomial is k multiplied k minus 1 to the fifth power, which means that if we win 2, we could see we could get 2. If we plug in 3, we get 96, 4, 972. So, and if we plug in, for example, 1, we're going to get 0. Obviously, this cannot be colored in one color. And 0, 2, 0, 0. Yeah, by the way, all the polynomials are divided by, can be divided by k, all for everybody, because you cannot color anything in 0 colors. Yeah. So let's talk about the coloring of a map. So what is the coloring of a map? We want to color a map in several colors. So no two countries that have the same border, the common border, have the same color. So for example, Germany and France have not the same color. Finland, Sweden, Russia and Ukraine, this should be the different colors. So, okay. So now let's take a general picture of map of Europe. So we can see there are several countries, like France and Spain have common border, and Portugal and Spain have common border. So let's make a graph. So we're going to make a graph. Each country is going to be a vertex, and we're going to connect them with the edge if they have common border. So as you can see, Italy and Australia connected, Czechia and Poland connected, United Kingdom and Ireland are connected. I just picked the biggest countries, not all countries here. For example, Turkey I didn't pick. I just took some of them and connect all of them. No, everybody that I took, I connect. So here is how the graph looks like. So when we remove the map, here is our graph. Okay, now let's talk about the four-color theorem. So the four-color theorem, first something like that was invented. It was called five-color theorem. It was invented in 1890. And the assumption was that any map can be colored with 5 or fewer colors in such a way that no adjacent territories have the same color. So that one was proved. And in 1976, there were assumptions that anything can be colored in 4 colors. So there is the proof, but it's computer made, so it's involved in computer algorithms, and people are still debating whenever it is we could take it or we couldn't take it, because in math it is still a highly debatable topic because you cannot really check the algorithms. So now let's color our graph from the Europe map. So as you can see, I was able to color this map in 4 colors. My colors are yellow, red, blue, and green. And you can check that no yellow two are connected, no green two are connected, no blue two connected, and neither are red two connected. So yeah, yeah, okay. So now let's talk why we were able to color why it is even possible to color any map in 4 colors. So a map is a planar graph, which is a special graphs that could be painted on the plane such way that no two edges intersect. So if you could draw a graph on the plane that no two edges intersect, then it's a planar graph. So as you can see on the picture, we have a planar graph that no two edges intersect, and that is why we could paint it in 4 or less colors, but not any graph we could paint in 4 or less colors. Actually, there is no minimum color. There is no minimum hue of G for like any graph. I mean, like if you take a general graph, there is no minimum hue of G. It could be like any number. If there is an example for each. So that's a planar graph, and that's why we even able to like do 5 for the less colors for map color. So now let's talk about chromatic number of a plane. In geometric graph theory, it is called Hagwin-Nielsen problem, and it asks the minimum number of colors required to cover a plane that not 2 points at distance 1 have the same color. So we color whole plane in some colors, and then we look at each 2 vertices, each 2 points of a plane on the distance 1, and they have to be colored in different colors. So if there are 2 that color in the same, it's not proper coloring. So there was such question, and we know that upper bound is 7 so far. So it means that we could paint our map in 7 colors at no 2 points on the distance 1, exactly 1, have the same color. So as you can see on the right, here is a bigger picture, the left smaller picture of the coloring, how we're going to color. So we actually do hexagons. In a hexagon, we color in 1 color. The radius of hexagon is a little less than 1/2. And this way, inside of hexagon, there is no 2 points at distance 1. And if we look at the same, for example, yellow colors, the distance between hexagons, the small distance is it's bigger than 1. So if the radius is exactly a little smaller than 1/2. So yeah, so this is the way mathematicians were able to color in 7 colors. So now I'm going to talk why 3 is impossible. So if you look at the picture on the right, you can see 10 points on the plane, and they're connected with the distance 1, exactly 1. So they're like right triangles and stuff. So I'm gonna explain why it's impossible for even these 10 points to be colored, which means that, oh, of course, a plane can be colored in 3 colors. So let's look at the left picture. Let's say that blue ones are not colored yet, and we're gonna color in green, yellow, and red colors. So let's paint the middle one in green. Okay. So now let's look at outside box, outside 6 vertices. They all connected to green. That's why they cannot be colored in green. Let's look at the left picture. So so let's paint one of them in red. Then next to it have to be in yellow. Next to the yellow that we just painted have to be red, because you have just 2 colors left. Next to the red that have to be yellow, yellow, red, yellow, red. So it's like that. We could switch yellow and red, but it's no real difference. So it should be colored like that. Now let's look at the middle triangle on the left picture. Let's see that they all connected, which means that they have to be all different colors, because if just be 2 colors in that triangle, then there will be at least 2 or 3 vertices of the same color, which are connected. So we lost. This means that they have all different colors, and there are 3 of them. This means that all of 3 colors, green, yellow, and red, have to be there. But if you look at the picture to the right, you would see that if you paint this way, then they're going to be, any way you remove it, they all connected to the red ones. See, they all, each one connect to one of the red ones. And we have to have 1 red. So it means that we're going to have 2 reds. So this is the example, this is the proof that we cannot color in 3 colors. So the actual lower bound so far is 5. So it means that it cannot be colored in 4. In 2018, a computer science and biologist found a 1581 vertex example that cannot be colored in 4. So it's a fun fact. He was not a mathematician. He was doing it for fun, and he found it, and he calculated on the computer, but that proof is accepted. And yeah, later on in the same year, it was found after, people start doing it, researching more, and they found a 553 vertex example in 2019, 510 vertex example. So yeah. Yeah, so the answer so far is unknown for the proper coloring of a plane, and it's between number 5, 6, and 7. So far any of this number could be. And here is an example of a graph that the first four non-colorable graph that was found. Pretty crazy, right? So yeah. So yeah, thanks for watching. I guess that's it for my lecture. Yeah, thanks.